Hello everyone, welcome to second part of the ENC28J60 tutorial series. At this part, we will do the full initialization of the module. Let us start with wiring the module. The wiring is very simple. You connect the SPI line, connect chip select pin, VCC and a ground, according to the QMX pinout. So on the STM board, SPI clock is on PA5, slave output is on PA6, slave input is on PA7 and chip select is on PD7. For the power line, you connect the VCC to 3 volt and the ground to the ground of the STM board. And for the interrupt line, for the interrupt pin, we will leave this unconnected for now, but I'll connect it in a later stage. Now let's do a basic SPI communication test. Let's try to read from one of the control registers, and if we got the right default value, then SPI communication is set up correctly. So let's read from the very first register, 00 in hex, and it's the Ethernet read pointer low byte. And by default, the default value of this register is FA in hex. So let's try to read from this. I've already written the code in advance just to save time. I'll just copy and paste it in here. So what this code is doing is that it's setting the chip select pin to low to activate it, and then we're sending the address of the register we want to read from, and then we just simply read from the SPI. This is the read operation is described in the datasheet in page 28. It says if you want to read from any control register, you simply send the address of that register with 000 as operation code, so the high 3 bits are already 0, okay, and then we simply read from it. So I've done this, but I just need to define this variable at the very top as unsigned 8-bit integer and array of 2 elements. That's it. So let's compile and upload the code and go to debug mode, and hopefully we'll get SPI data 1 as FA. If we got this value, then SPI communication is working correctly. Okay, I'll upload it to the board, and we'll go to debug mode. Click OK, and this will take us to the debug window. Now the very first thing we need to do in here is we need to add the variable into the watch memory so that we'll be able to watch it in real time. So it's already added, and it's an array of 2 elements, so you can see the first and second elements. And we are interested in the second element because that's the element that the SPI store the data in. So let's run the code line by line until we get to the receive. Perfect, so we got FA, and that's the default value of the read pointer register, and it's FA. Let me just show it to you quickly. It's this one, RDBTL. It's F and A in hex. So having got a successful SPI communication, the next thing I want to do is that I want to define high-level functions for read and write operations. So instead of doing these low-level steps all the time, I just define a function that does this, and I just pass the parameter and the address, and it does all this in low levels. And to do this, I will create header and C file. The function prototypes will go in the header file, and the function definition will go in the C file. This is a very basic C library structure. So let me add a new header and C file. Header file, I will call it ENC28J60 J60, and maybe STM board at the start. Okay, and I'll add this file. I also need to add a C file. I'll call it the same name, J60. So on the header file, I'll define my very first function. I'll call it unsigned integer rate, committee, and ENC28 read register or read operation. Now the read op function needs to have 2 parameters passed to it: the operation you want to implement and the address to read from. And as described in the table in page 28 in the datasheet, that we've got 2 possible read operations, either to read from a control register or to read from the buffer memory. So we'll pass parameter as unsigned integer rate oper as an operation and the address to read from. Alright, now we also need to include the STM header file. Okay, now let's just compile the code and just to make sure that we've got no errors. Right, perfect, we have no errors. Now let me define another function for the write operation. So it will be similar to this, but it does not return any parameter. And let me copy this. It will be ENC28 write instead of read. Alright. This function will take three parameters. It takes the operation, address, and also the data to write. Just written it in advance, so let me just copy and paste it. Right, perfect. Now let me add few more functions that are very specific to control registers. I'll add them first and then I'll explain them to you. I copy and pasted them. I've added four functions. This one to read from an 8-bit register, to write to an 8-bit register, read from a 16-bit register, and write to a 16-bit register. They are useful because I don't have to specify the operation all the times. And as you can see, operation is not a parameter of any of them. Now we need to add one more function and we should be good to go. And this function I'll call setBank. The reason for that is because let's look at the datasheet. The datasheet split the register into 4 banks, bank 0, 1, 2, and 3. So if you want to read or write, if you want to access any of the register in bank 0, you first need to set the bank to 0, and then if you read or write to, for example, 02, it will be this one. If the bank is 1, 02 will be this register, and so on. And as you can see, the last 5 registers are common to all the banks. And to change the bank, you need to write to control register number 1, I think. Okay. So let me write the function. Call it setBank. I hope this makes sense to you. If it doesn't, later on I think it will make sense when we do it there. Okay, so the bank will be just a number. I'll write bank number. Alright. Now let's go to the C file and define the content of each function. Let's copy all of them and paste them into the C file. But we also need to include the header file of the library in the C file. So I've written it in advance. Let me just copy and paste it. Right, paste it in here. So perfect. Now let's define the content of each function. The read-op function is exactly similar to the one we defined in the main earlier on. It's this one. So let me copy and paste it. It is, we set the chip select pin to low, and then the first data we send is a combination between the operation and the address. So we need to shift the operation 5 times. I'll explain this now. And we do the OR operation with the address. Okay, if you didn't figure out why it is the case, let me show you in the datasheet. So according to this table, the read operation is the last 3 bits, or after 5 bits comes the operation code. So that's why we shifted it 5 times to the left, and then we did the OR operation with the address. Now we need to declare this variable SPI data, so I'm going to declare it at the very top here. Unsigned integrate T and SPI data 2. So it's just a local variable here in this function. Now we also need to declare this HSPI type diff, but this one is defined and this one stores the SPI configurations. So I'll just copy and paste it from the main. I'll define it as an external. And the reason why I define it as external and I didn't declare it from scratch is because this one stores all the configuration and initialization setting for SPI. That's why I need to just use external so that it gets the same configuration as the one in the main. Now we need to return the read data, so return, and the read data is SPI data index 1. Simple as that. Now, let me define the other functions and I'll explain them to you. For the write up function, it does similar thing at the start. We declare this variable, and then we combine the operation with the address, and we store the data in the first index, and then we transmit both of them, one after the other. Unlike this one, we transmit the first byte and we receive in the second byte. This one, we are transmitting a data, and then we set the CS pin to high to disable the SPI. And you don't have to worry about copying and pasting the data because I'll provide the H and C file down in the description of the video. For read_reg8 function, to read an 8-bit register, we first set the bank according to the address. Don't worry about this for now. I'll explain when I define the setBank function why just passing the address would be enough to specify which bank this address belongs to. Okay, and then we call the read_op function, the one we defined at the top, and we pass the first parameter as read control register, and we defined it in the H file as 00, for the same reason as I explained before. In this table, to read control register, the operation has to be 00 and hex. Okay, back again, and then we pass the address, and the returned thing we also return it to this function. This is very simple. It's just a higher level function to the read_op function. Now, the write register rate would be very similar. We set the bank first, and then we call write_op function, and we pass the address and data. And this one we already defined as a constant write control register. We defined that in the H as 0x20, because in the table to write control register is 010, which is 2 in hex. For read register 16 function, we call read_reg8 twice. The first time we read the lower 8 bits, the second time we read the higher 8 bits, and then we combine them in a single 16-bit variable and we return them. We do a very similar thing to write reg16. We call write reg8 twice. The first one we write the lower 8 bits, so we have to do and 0xff to write the lower 8 bits, and then we write the higher 8 bits, so we shift it by 8, and then we do and ff like this. So we increment the address by 1 to go to the high 8-bit address, and we write the high 8 bits. Now, for setBank function, we pass the address as a parameter to setBank, and then it needs a way to figure out from the address which bank this address belongs to. So I think it makes sense to change the bank number into address. We'll also change it in the header file. Okay, I think that's a better name for it. Now let me go to the header file. I'll add a few variables that are useful for this function. So I've copied them. Let me paste them in here. So here's what I added. I've added a few extra operations defined. This defined bit field clear and bit field set operation as in table on page 28. So these are part of the write operation. You can write to a control register, you can write to a bit field set and bit field clear in the control register. Okay, that's what I defined here. And I have defined some mask and constant. I'll come back to them in a bit. And I have defined the control register of each bank. For bank 0, these are the control register. For bank 1, these are the control register, and so on. And what can you notice? In bank 0, I've just added the plain address. But for bank 1, I've added this extra bit to it, 0x20. And for bank 2, I've added 0x40. For bank 3, I've added 0x60. And the reason why I've added this is so that when I call the set bank, from this it can figure out that this control register belongs to bank 3, alright, or other register belong to their other banks. And I have defined the common register without any bit, because these are common to all the banks, regardless which bank we are in. These are still valid. Then I have added bit field defines. These define the bit field number 1 and bit field number 2 of econ 1 register. So let's go back to the set bank and define its operation. And now you will understand why I've defined them Just bear with me a minute. The first step, we check if the bank we want is not equal to the current bank. If it doesn't equal to this, then we need to set this bank. Okay, and what can you see? I did AND operation with the bank mask. So bank mask is this. And what bank mask is effectively doing is that it separates the register address from the bank specific bit. So when I remove this one, all is left is this bit. This one will have got nothing left, this one will have this thing left, and so on. So set bank function can define according to this which bank this register belongs to. And this variable ENC28 bank is I define at the top to store the current bank of the registers. Okay, we change the bank from econ1 register. So let's look at the data sheet. Econ1 register field 1 and 2 are the one that determine the bank select. Alright, so first step, we will use write up function to clear those bits, and then we will write the new bank we want, and after that we will store the new one in the current bank variable for later use. That's pretty much everything in the set bank function. These are all the functions we need to be able to do the basic initialization. Now let's go ahead and do the initialization. But instead of doing the initialization in the main and calling function by function, I will create a higher level function. I will call init. I'll call it void ENC28J60 or just 28 init, stand for initialization. And I'll call it in the main, and I'll do everything in the body as function. So let me just copy and paste it and put it in the C file and do all the initialization inside here. The first step of the initialization is to disable the SPI line by setting PD7 to high. The second step is to perform soft reset, and this is described in the table in the datasheet. To perform soft reset, the first byte of the argument is 1F and the operation code is 7111, just like in here. This one is defined as 7 in the H file. And then you wait for 2 milliseconds. Sorry, this one should go here. This is just the data, but this one has got no data in it because in the table there is no data, so I'll leave this one 00. The third step is to wait until the clock is ready to use. So we read from stat register and we check for the bit field stat clock ready. Let me show you in the table in the datasheet. So looking at the stat Ethernet status register, it says that bit 0 is the clock ready bit. If this one is 1, then the clock or the physical clock is ready to use, and that's exactly what we do in here. The fourth step is to initialize the RX and TX buffer size. I set the start of the RX buffer at 0 and the stop at 0x0BFF. This can be shown in the datasheet at this figure. You can split the Ethernet buffer into TX and RX, and I said I want the RX buffer to be from this address to 0BFF, and the rest would be as a TX buffer, which I'll do in a minute. That's the TX buffer. I say the TX buffer is from just one bit after this one, so 0C00 until 11FF. That's my TX buffer. Now I also need to set my RX read pointer to the 0 position and also my RX write pointer to the 0 position. So the read pointer is the pointer in which STM board read from the buffer, and the write is the MAC layer. When it receives a packet from the router, it writes it to that RX buffer. So I just set them to 0, and then you'll understand what they mean later on. Next is the receive buffer filters. And I said I want unicast and CRC. Let's go to the ERX FCON register and I'll explain what they mean. So this Ethernet receive filter control register, and this has got many filters, and I just said I want to enable 2 filters. I want the unicast and the CRC. Unicast mean only packets that has got my MAC address will be accepted, and CRC only packet with the correct CRC will be accepted. And I enable the AND bit so that I want this and this, not one of them, not just all. Okay, and that's the code for it. Next is MAC control register number 1. And at this I said I want to enable the RX, I want to enable TXpose frame, RXpose frame, and I want to pass all the received frame if they're not filtered. This is described in the datasheet and the MacCon1 register page. So I said I want to enable receive buffer. So here I'm telling the device, besides transmitting packet, I also want to allow it to receive packets. Then I said pass all the received frame and store them in the RX buffer if they are not filtered. Then I enable RXpose frame and TXpose frame. If you don't know what TX and RXpose frame mean, just Google pose frame Ethernet and they will explain them to you. Alright. Next is Mac control register 3, and I want to do some few more settings here. And what I said I want to do is that I put the pad CFG2001, which means that all the short frames will be 0 padded to 60 bytes and a valid CRC will be then appended to them. This is a very useful feature, so that I don't have to worry about CRC, it will be done automatically. And this, I also need to enable this one so that this one will be true. To transmit CRC enable bit. Then I said I want the frame length checking enable bit. So this will check the frame length. If it's very short, then it will ignore it. Okay, that's what I did here. So, and frame length. Next is something called none or back-to-back gap. And according to the datasheet, we set the in most application the low byte is set to 12 in hex and the high byte is set to 0C in hex. So I did that, 0C and 12. And next is the back-to-back gap. According to the datasheet again, it says set to 12.5 duplex mode. At the moment, we enable SPI full duplex, but we're still operating in the half duplex in the Ethernet module. So we set this one to 0x12 in hex. I just made a silly mistake. This one is supposed to be 8 bits, not 16-bit register. And next is this is the maximum frame length. So I set the maximum frame length to 1500. So any received packets that are bigger than this will be discarded. This is something just a limit because I don't have enough memory. So any long packet will be discarded. And this is the same setting we set in there. We enable the frame length thing so that if the frame length is bigger than the maximum, it will be discarded. Next is to set the MAC address of the device. MAC address is usually a hardware defined number, but for the ENC28 this is you define it in software, and it is a 6-digit number. So I define it in the header file, 6 digits, and then I write it to the registers. And the ENC28 has got a register for each digit. So MAC digit 6 is in register 6, and so on. This is the basic initialization and it's all done. And the next video I'll do the advanced initialization. The advanced initialization are slightly more difficult and require adding a few functions in the header file. Okay. But before I finish this video, let me read some of the register I've written just to make sure that the value is gone correctly. For example, I'll read the MAC address number 4 and see if I get the MAC 4 value. Alright, let's do it. Let's compile the code and upload it to the board and go to debug mode. Compiled successfully without any errors. I need to call this function, by the way, in the main. Compile successfully without any errors. And by the way, I need to call this function in the main. Let me just copy in the main. I'll just comment this one and I'll call it just in here. I need to include the header file in the main to be able to use the function. Let me just copy and paste it quickly. That's it. Now we're ready to use it. Just compile again and upload it to the board. Now let's go to debug mode and see if we can get the same value. Let's run the code up to here and then we will enter step by step. I need to add this variable to the watch memory to be able to see the value in it. Now let's run the code step by step until we get to the one for the MAC address. I'll actually just skip it. Perfect. Let's go to this one. We got 80. Is that a right value or not? No, this value is wrong, so there must be something wrong. Let me double check and I'll come back to you. Alright, after few debugging, I found few mistakes and I have added some parts to the code. The main part I have added is this, to some of the registers. Because I found some of the registers, in order to read from them, you have to call the receive function twice. This is shown in this read operation function. So, I've added 80 to those registers, and this function will check for this 80. If the address of that register has got this, then it will call the receive function twice. Okay, and I have corrected some of the mistakes here, and I have added some functionalities. You don't have to worry much about what I have corrected and what I have added, because at the end of the video I'll provide the HNC file down in the description. So let's do our test again. I will check the data of one 16-bit register, which is the ERXND, and I will read all the MAC addresses, the 6 bytes of the MAC addresses, and hopefully I'll get the correct value. For this one I expect to get this RX top, which is 0BFF as I've defined it here, and for the MAC addresses I expect to get those 6 bytes of the MAC address. Okay, so let's compile the code, upload it to the board, and go to the debug mode. We are in the debug mode now. The first thing we need to do is to add the two variables that we want to watch to the watch memory, and that's the data watch 16 and the data watch 8. So let me add them to watch 1, and now we can run the code up to the breakpoints. Okay, so up to the breakpoint, one step in, perfect. I got 0BFF just as I would expect. Now let's check the MAC, the bytes, the 6 bytes of the MAC address. The first byte I get 36 in hex. Does that match with the one I expect? Yes, perfect, 36. The next one I expect 30, and I got 30. Next 2D, then 69, then 69, then 74, all in hex. So next one is 2D, then 69, 69, and 74. So perfect, we're getting the right value. It seems like our basic initializations are all working correctly. That's all for this video, and in the next video I'll start with the advanced initialization. Thank you.